but also these were the first carbon cycling studies in coastal Louisiana. He worked in the University of Georgia Marine Institute for 10 years, and then in the Marine Biological Laboratory, Ecosystem Center at Woods Hole for 20 years. During this time, he was the lead PI of the land margin ecosystem research at Plum Island Sound Estuary, which became part of the NSF current long-term ecological research program. Also during his tenure in the University of Georgia, he was the first NOAA Sea Grant Director for 8 years. There, he introduced a new coastal recycling program, which earned a popular best extension program denomination by the U.S. Sea Grant Network, which was bought by the Sea Grant Extension. There, he has taught in the University of Georgia ecosystems biochemistry and introduction to coastal ecosystem at the University of Georgia in both the undergrad and graduate programs, including independent research at Sapelo Island during the summer. He has published more than 160 papers, including publications in the journal Nature, where he revised the carbon cycle of coastal ecosystems, the non-Redfield ratio dynamics of dissolved organic matter in the world's ocean, and exporting carbon mechanisms at the boundary between the land and the coastal ocean. Dr. Hopkinson is now retired. He retires in January 1st, 2020, but, and I'm gonna quote here, is still in office, is still teaching, just without pay for the most part. Chuck, the floor is yours.
All right, thank you very much, Victor, for that introduction. And in honor of my getting that National Sea Grant Reward for the best extension program. Say what? No, it's on. You can, yeah. I was actually removed from the Sea Grant program because it smacked too much of climate change. And of course, in Georgia, climate change is a little iffy, Okay, so some people say that, like wine improves with age, and John was also saying something about improving with age. Would you buy that? Okay, so at the end we'll have a test to see who knows everybody there, and I'll buy a beer for the person who can get them all. So luckily for me, I started in September, August 1971, and at Christmas time I ran up against this guy, and he had me working on his carbon budget synthesis that he and Jim Gosling and Gil Smith and a few others were putting together. And it just changed my way of thinking. And from then on, I just became so interested in systems, biogeochemistry, and aquatic systems that, I've never had a day, a Sunday or a Monday where I didn't want to go to work. So move on to the next one. Guess I have to aim it somewhere to make it work. Okay, so there we go. So here's a seminal paper about metabolism of the coastal marsh. It was produced by John Teal back in 1963. He was hired straight out of graduate school, having completed a study similar to this for a cold spring in the north at the same time that H.T. Odom produced his for Silver Springs. And back in those days, everybody was interested about kcals per meter square per year. And a couple things that I want to point out that we'll come back to is the rate of NPP on here, 1463 grams carbon per meter square. So I made the conversions for you, and NEP of 816. So the net primary production of the marsh was supposed to be close to 1,500, and 800 of that was available for export to the water bodies. So that's about close to 50%, 44%. And then when I got to LSU, this is what John was working on, and this is what he started to get me working on also. So here's the same thing for the marshes at Barataria Basin, and he has the production of the marsh and the water. So Teal looked at just the marsh, John here is looking at the marsh and the water, how they integrate, how they feed each other. And again, he came up with an estimate of what the net primary production of marsh was, similar to teal. He came up with an idea of how much was exported to the water, about the same percentage that teal concluded in his study for the Sapelo marshes. Okay, so where do I come along? So I start with John. He has me working on that project. And the first thing I hear about is the outwelling hypothesis, which Gene Odom coined back in the 60s. Teal was Gene Odom's graduate student, postdoc. And he concluded that this excess carbon in the salt marshes was exported to the tidal creeks. There it became part of the detrital food web. It was decomposed, and it contributed to secondary production. Scott Nixon, a few years later, a decade and a half later, he was from the Northeast. He was working in Rhode Island. The fisheries up there are largely, demersal fisheries offshore from the continental shelf. They do not have that estuarine dependence quite like the ones in the Southeast and the Gulf of Mexico. So he questioned this whole thing about export of organic matter from salt marshes and how important they were for fisheries production. And, being a salt marsh dominated type estuary person, I wanted to look into that a little bit more. And I conducted another analysis that was published in 1988, where I looked at about a half a dozen salt marsh dominated systems along the East Coast and the Gulf of Mexico, from Flax Pond down to Barataria Bay. And it's like all these systems export substantial amounts of organic matter. Trying to come up with a common denominator that would enable you to predict how much is coming out and what form, that was impossible as a result of my studies. So from there, I went on up to Woods Hole, and I got involved in these LMER and LTER projects. And there we were kind of questioning, well, how does this marsh-derived organic matter actually support higher trophic levels, especially with a microbial loop out there, which was then the big research question, which is very inefficient. There are a whole lot of food web steps along the way to get carbon up to higher trophic levels. And especially when you have all this allochthonous stuff coming in from the marsh and the watershed that has a very high C to N ratio to grow biomass that's about 6 to 1, you need a whole lot of nitrogen. So there's competition for that inorganic nitrogen. And then the last thing I got involved in that was also related to metabolism was this National Academy study. It was a 2-year study, and we were looking at, well, it ended up being called negative emissions technologies. So that included blue carbon and included agricultural practices to sequester carbon in soils, et cetera, et cetera. So what I'm going to talk about today is going to end up with blue carbon and how can metabolism better inform us about blue carbon. The paper that started this whole subject matter of blue carbon is this one that Lizzie McLeod led, and it had Gail Chamorro. Gail spent some time down here. Carlos Duarte, he's an expert in seagrass ecology. Many of you here probably know of him. And then Wild Bill Schlesinger is a terrestrial biogeochemist, and he brought that global perspective into this study. And what was really interesting about their study is they pointed out that the storage, the accumulation of carbon in soils in these individual ecosystems was order of magnitude higher in these coastal systems than it is in tropical forests, boreal forests, temperate forests, okay? And then even those salt marshes and mangroves and seagrasses have, very, very small areas on the globe. So here we have areas, square kilometers. So this is an estimate that Lizzie McLeod and I put together in 2020 for this EFI white paper. And so I think these are the best numbers that you can come up with, the aerial expanse of these things. And then we use these most approved rates of burial, grams carbon per meter square per year, to calculate what the annual burial and sequestration of essentially atmospheric CO2 in the soils was. And it's about an order of magnitude less than people at the time really thought it was going to be. Instead of 0.1 petagrams per year, that's 10 to the 15 grams. Instead of 1, it's only 0.1. And by way of reference, we're releasing to the atmospheres on the order of 7 to 9, something like that. Okay. what hasn't become part of many budgets, but which was also identified in this paper, was the fact that a lot of our marshes and our seagrass and mangrove systems are washing away. They're sinking. So the two sites I'm going to talk about today are these two sites that I've worked extensively in. One's the Georgia coastal ecosystems, the systems around Sapelo Island in Georgia, and then the Plum Island system. So PI stands for Plum Island Ecosystems, LTR. So here's the Plum Island system. The things I want to point out here is the high ratio of marsh to water, so 2.4 to 1. The macro tidal system, 2.9 meters. What you have about this much, and up there it can get up to 4 meters. The other thing that's very interesting about this particular system is, well, it's cold water, so it's in the Acadian biogeographic province, and the marsh platform is very high. So 49% of the marsh is above the mean high water mark. Okay, now we can here's what the marsh looks like. So it's dominated by Spartanopatens. It is cold. John would love it up there. And the marsh is breaking apart. These are ponds that are forming in interfluvial areas. Starting back in the back in colonial days, this area was heavily ditched because, well, I'm not going to go there. There's too much to cover. Okay, now the Duplin has an even higher marsh to water ratio. It's 2.7 to 1. It's a mesotidal approaching macrotidal with an average 2.2 meter tide. And it's much lower in the intertidal frame. So when you look at this hypsometric graph, only 9% of it is above the mean high water mark. And like Louisiana, it's a bit warm here. And this is what the salt marsh down there looks like. So one of the things I want to point out here is this eddy covariance flux tower. That's really revolutionized our ability to be able to come up with good carbon budgets, measures of production and respiration for salt marshes. This is a tidal creek immediately adjacent to the flux tower, and this dead area is actually an evidence of headward creek erosion that's occurring pretty dramatically in the marshes there. Julia has been working in well, he's worked in both of these systems, Plum Island and Sapelo Island. Okay, so I'm going to present all my data in a format like this, where I have the marsh separated from the adjacent water column. So we have the atmosphere up here, and the flux towers are actually measuring the take-up of CO2 by autotrophs, by the primary producers, and the release of CO2 by the heterotrophs on the marsh. So the balance, but they're directly measuring net ecosystem exchange. So net ecosystem exchange means the exchange of CO2 with the atmosphere. It does not mean net ecosystem production. In conjunction with measures of lateral transport of dissolved inorganic carbon, we can calculate what the true respiration, because the flux tower only sees that which is going up into the atmosphere, but every time the tide comes up onto the marsh, it's picking up some dissolved inorganic carbon, call it TCO2, whatever you want, and then it's exporting it back into the tidal creeks in some systems. So that we have to take that into consideration when we calculate respiration. So here we have GPP of the marsh, respiration of the marsh. The balance between those two things is net ecosystem production, right? Okay, there are two fates of this net ecosystem production. Some of it can be buried and some of it can be exported to the adjacent tidal creeks. Other processes that are occurring in the marsh that I'll discuss are deposition of organic carbon that's in the water column at one stage of the tide, goes up onto the marsh and settles down. So that's an additional form of carbon that pretty much nobody pays any attention to. And then edge erosion. We've actually quantified edge erosion or erosion rates in both of these two systems that I'm going to study. The organic carbon export is calculated by mass balance. Everything else here is directly measured. Okay. And then in the water column, we're we have measures of river organic carbon load, how much flocculates, how much is consumed, how much passes through unprocessed. And then we also have measures of gross primary production of all the autotrophs in the water column and the benthos, respiration of all those. This is done with measuring DIC over time and measuring dissolved oxygen over time. And with that, we can calculate net ecosystem production, and solving the mass balance, we can calculate how much must be exported to the ocean. And then we can also measure how much, so salt comes into the estuary. When salt water comes into the estuary, there's also DOC. So there's some consumption of that DOC while it's in the estuary. So I've calculated that also. Here's a flux tower. This is the flux tower that's set up at Plum Island in the wintertime. It's up on top of this little drumlin that stands about this high. And it's near the middle of a marsh site, an interfluvial area where the flux tower goes in the summertime. But this enables us to get, even with those icy conditions, we can get the full measure of metabolism. This is what measures of the metabolism look like that come from a flux tower. Whoops. So the units here are micromoles of CO2 per meter square per second. So each of these is a per second measure for 3 years. Okay. From that, we can calculate what the cumulative net ecosystem exchange for the atmosphere is. So just to go through this with you. So during the first 4 months of the year at Plum Island, there's a net release of CO2 to the atmosphere. So essentially there's nothing green from the end of September until sometime in April. In April, you start to see Spartina patens and Spartina alterniflora sprigs about that high. But there's still metabolism going on in the soil, in the sediments. And then as soon as it greens up, CO2 is taken up. And over the course of the whole year, the system has taken up more CO2 than is released to the water column. And then we can break it down the way we normally would do when we take monthly field trips, and we can show what the net ecosystem exchange rate is for each month from year to year to year. And we can also calculate what the rate of GPP is, and we can calculate what the rate of respiration is, and then calculate the net. Okay, so how do we get some of the numbers for the aquatic system? So here's a picture of the Duplin again. And for this particular study, we had 12 stations along the length of the Duplin, and we measured, I'm just going to show some seasonal data from this. So here's for August. So from these transects, we could measure what the PCO2 concentration along the length of the estuary is, and what the dissolved oxygen levels were along the length of the estuary. We do this at dawn and dusk, which enable us to calculate metabolism. And then just knowing what the concentration is relative to saturation levels, we can calculate how much is exchanged with the atmosphere. And from just the downstream gradient of, well, that's not DIC, so I'm jumping ahead. Here's a plot of just the DIC from these different seasons, and it's from this that you can actually calculate what the rate of metabolism is after you correct for air-sea exchange and for lateral export, lateral dispersion and all. So in all cases, you can see there's a downstream gradient. This is closer to the ocean here. This is up at the top of the estuary. And then from that, here's just an example for August of how we calculated GPP, respiration, and net ecosystem production. Okay, we also spent a fair amount of time trying to figure out what's happening to the water when it goes up into the marsh, especially the marsh that is flooded by this tidal creek during high tide. So this is a topographic shading here. So here's the tidal creek that comes up. The flux tower is right about here. So we would monitor at a station out here what the DIC and the pH and the total alkalinity and that stuff was, so that we could determine what goes on when that water gets on the marsh, et cetera. And this was really interesting to me, and it still is, and I tried to get a postdoc interested in following up, but she became too involved in other stuff. But anyway, from that study, we were able to calculate how much DIC is exchanged with the marsh So in these 4 months, 4 out of the 5 months, DIC was exported from the marsh. So it comes in with about 2,000, 3,000 micromolar DIC. It picks up a little extra DIC because, I mean, the DIC concentration in the pore water is up to 20,000. So some of it gets into that water and is exported. In 1 month of the year, in October, very sunny day, this was only a 12-hour single tidal study. There was actually a net uptake of DIC. The air-water exchange was very revealing. At all times, the water's supersaturated when it comes up into the marsh, and it degases, as you'd expect. When we combine that with how much is leaving the system when it's over the marsh versus how much is in the tidal creek, in that particular tidal creek, you can see that, so the marsh, here's the brown is the marsh water, the blue is the tidal creek. There's a lot of CO2 leaving per meter square when it gets up onto the marsh. And then when you scale that up to the entire estuary, you take into consideration that, the marsh water ratio is about 2.5 to 1. There's a lot of CO2 that leaves the system just when it's up on the marsh, somewhere between 14 and 36% of it. And the way we calculated this, I mean, we used an oceanic air-sea exchange equation, and we use the intercept value for totally calm conditions to estimate what that CO2 exchange was to the atmosphere. So what the appropriate gas exchange coefficient should be has yet to be evolved. So determined, this is just assuming a baseline level, the lowest level that is typically used in aquatic systems. And then we can put all this stuff together and come up with a carbon or an oxygen balance, where we take into consideration what the exchange of CO2 is with the atmosphere or oxygen when it's over the marsh, how much DIC is exported to the tidal creeks, the total CO2 released to the atmosphere, and calculate how much goes to Doughboy Sound and ultimately to the ocean. Okay. How do we get burial rates on the marsh? The way everybody does, we look at in both these studies, we used both cesium and lead-210 and calculated what the burial rates were. So they range from about 110 to a minus 112 at Plum Island for this particular site. Accretion rates, 0.3 to 0.49 centimeters per year. Yeah, okay. The other thing, recognize this photo, Julia? Okay, so an important process up at Plum Island is edge erosion. So we get these scarps, high tide, mid tide, the water is up against there. There are these little waves that are always breaking against these surfaces. It undermines and the stuff falls out onto the tidal flats. So we wanted to quantify how important this erosion is and what the ultimate sources of inorganic sediment are that get up onto the marsh to support it. And so we came up with this approach where we had 2 LIDAR data sets, one from 2005, one from 2011, 1 meter resolution. So we could come up with, this is just an example of a couple transects across the LIDAR data set, and the elevation in 2005 and the elevation at the same transect in 2011. That volume, that shaded volume, is the volume of sediment that was lost in a 1 meter wide band at the shoreline. Okay, when I put together this budget, it turned out, as far as the ultimate sources of sediment, we couldn't account for most of it. The river only supplied 9%. The erosion had the potential to supply 27% of the inorganic sediment, and the rest is a mystery. So here it's just defined as the ocean. It could also just be deepening erosion and deepening of the tidal flats and the tidal flat water going, the sediment, the resuspended sediment going up onto the marsh. And of course, the deeper the tidal flat gets, the worse the erosion gets. So it's kind of a positive feedback there in the wrong direction. Okay, here's the budget for the Duplin River estuary. All the numbers. So these are standard errors. That's what you see here. Something that I didn't mention before is these units are relative to a meter square of marsh. So the rate of primary production, 768 grams carbon per meter square per year. The export, on average, there's 126 grams of carbon exported from every square meter of the marsh surface. When that gets into the water, because there's 2.5 times more marsh than there is water, that number is amplified. So 126 converts to 126 grams from every square meter of marsh, then becomes the same as 295 getting to every meter square of the water column. Okay, so now that you've memorized these numbers, let's break it down so it's a little bit more palatable. How am I on time? 11:58. Okay. So let's first look at GPP. So GPP is, so we have Plum Island here and the Duplin on the top. Probably should have reversed it, being that Plum Island's north. So the GPP is higher at Plum Island than it is in the Duplin, 914 versus 768. Think back about John's number and Teal's number. They had 1,500 grams carbon. So we're only having half of that. This is very surprising. It's still very surprising to me. Respiration, however, well, here's the rate of respiration. It's about 70 to 80% of GPP. So that's very different than, so the level of respiration is similar to what they found in Louisiana and Georgia, John's and Teal's study. But relative to the rate of primary production, it's a much greater percentage. The PR ratio for both of these systems is very high. So here it's 1.2 times more primary production than respiration for the Duplin, 1.4 times more production than respiration there. So they're the green circles. Now let's go to, well, the respirations are the red circles. We already talked about that. The net ecosystem production is a little bit higher in Plum Island, 259, than it is in the Duplin. The lateral flux of DIC requires a little bit of explanation. So like I said, the flux tower is only measuring what exchanges directly with the atmosphere. Well, some of that time, water at high tide goes up onto the marsh and it's degassing CO2, and that's picked up by the flux tower. So we have to quantify what that is and subtract that from what is seen by the flux tower so that we can determine how much is just coming from the marsh itself. All right. The other thing that's happening is when the water is up there, it's gaining DIC and it's exporting DIC back to the tidal creeks. So there's 65 grams carbon per meter square being exported in surface water to the adjacent tidal waters. So we have to take those fluxes into consideration to recalculate from this net ecosystem exchange what the true net ecosystem production is. So after we know what the true respiration rate is and the GPP, we can calculate the NEP. Okay, so that lateral flux is very important component here. The other thing, as a result of that sediment budget paper, I was able to translate that in terms of carbon also. How much carbon is going up onto the marsh? So when we know when we do our water column sampling, we know what the TSS load is. We can calculate how much of that is POC, et cetera, et cetera. So when the water is up there and it's dumping out fine grain, silts and clays, it's also dumping POC. And when you put filter papers out on the marsh surface, a lot of what you're collecting is what came up with the tide and settled out, and a large percentage of that is POC. So we've quantified that right here. And it's equivalent to about 20% of the organic carbon burial at Plum Island, that import of material from the water column that gets deposited on the marsh. And actually, that's a study that you're doing with Amanda. So Amanda has looked at a number of biomarkers, so she can document the effect that for the Duplin, for Plum Island, that a certain percentage of that carbon is the eroded carbon from these old creek banks. So it could be 2,000-3,000 years old, because these marshes started accumulating about, what do you remember, 1,300, 1,400, 1,500 years ago? That's the basal peak. Yeah, Plum Island. Or 3,000 years? Yeah, so 3,000 years. So we're eroding some of that material, and the 14 carbon dating of the surface sediments, we're seeing some of that material being deposited on the surface. And on a budget wise, it turns out to be about 20% of the carbon that's currently being stored. Okay, the fate of NEP. So what happens to this NEP that John and Teal just assumed was going to the tidal creeks? Or I think John, his paper says it's available for the water column. Note that they, at that time, even though we were spending a fair amount of time trying to come up with some sea level rise graphs, because I remember working on some of that data with you, and we had some offshore oil platforms, and we were looking at what the rate of sea level rise was. It didn't go into your budget, the fact that carbon was being accumulated in the sediment that had anything to do with maintaining elevation. So anyway, organic carbon burial, it's much higher at Plum Island than it is in the Duplin. So here's burial, 111 grams carbon per meter square per year is buried in the Plum Island marshes. It's only 27 grams per meter square in the salt marshes in Georgia. Why the difference? Good question. Both of these systems are keeping up with sea level rise. So the accretion rates are 3 to 5, here I say 3 to 5 millimeters per year. The burial of marsh NEP is crucial to maintaining elevation. I mean, it's almost a peaty soil in places that gets up to 40 to 50% carbon. And as my budget showed, it's really sediment starved. And up to 20% of that is derived from the erosion of old peat, as I just said. In Georgia, the rivers supply much more carbon, much less than they used to historically, because the rivers are so heavily dammed. But about 2/3 of the sediment that's needed is supplied on an annual basis from the rivers to coastal Georgia. So that's that Herb Wyndham paper that came out sometime in the last year. So what else do we have here? Export. So export is the excess. So export of NEP is high in both these systems. It's especially high in magnitude at Plum Island, 190 versus 126 in the Duplin. But on a percentage basis, a greater percentage is exported from the Georgia system, 89%, or 126 out of 141 grams available. At Plum Island, 73% is exported relative to 259 be available. Again, what are the mechanisms contributing to these differences? So the other thing that's not included in any budgets that I've seen yet deal with this erosion and the input of allochthonous inputs from outside the system. So here's the allochthonous input. So it's 42 grams carbon per meter square per year is coming from the water column onto the marsh. Here's the erosion. So they're of a sufficient magnitude relative to the overall budget to make a difference. That's not quite such the case in the Duplin. The suspended solids concentrations are much higher, but the actual carbon content of that is a lot lower. So the POC input is lower, and there's very little edge erosion. It's almost in balance. I mean, there are places where it's eroding, but there are other places where it's building. There's a lot of creek bank erosion and then deposition on the opposite side, you know, on these meanders. Would you agree with that? Okay, good. So erosional inputs, they're small, but they strongly influence the budget at Plum Island. Let's leave it at that. Okay, let's go into the aquatic systems. So the P for both of these is reasonable, about what I expect, 297 for Plum Island and 407 for the Duplin River. John's numbers were 900 grams carbon per meter square per year. For Barataria Bay, I kind of question that at this point. These numbers are very reasonable for this system. There's been there were a lot of C14 studies back in the 70s and 80s, and there was a lot of C14 both in the water column and the benthic microalgae on the intertidal flats at low tide. And these numbers are derived from our metabolic surveys of inorganic carbon and dissolved oxygen. So it doesn't separate between the water column and the benthos. But it's a nitrogen limited system, and it's very turbid water, so it's also light limited. The river organic carbon, they're also extremely heterotrophic. So the PR ratio is 0.57 for Plum Island, it's 0.66 for the Duplin. River organic carbon is relatively unimportant. 0.4 to 4.8% of respiration at Plum Island and probably less than 1% at in Georgia. So in Georgia, there's no direct river input to the Duplin River. So the rivers come in, they dilute it, they dilute the coastal zone with fresh water. Some of that fresh water gets up into the Duplin River because the salinity in the spring will go down to 20 ppt. So, we can calculate on the basis of how much fresh water is in there, what the DOC and freshwater input in the river is, what the residence time of water is in there. So we can make that's how we determine how much of that river carbon is actually taken up. In Plum Island, it's more straightforward. We have a river that comes right in the top. I've made the assumption that all the POC and 10% of the DOC settles out and is deposited here or there. I mean, estuaries are sediment traps. We have a typical estuarine turbidity maximum zone up around 2, 3, 4 parts per thousand in the upper estuary. But out of 185 grams carbon per meter square per year coming into the river, only 8 is actually consumed by DOC, because the residence time, well, first of all, it's only like 10 to 20% labile in the time frame of estuarine transport, but it transports through so quickly, very little of it is actually taken up. The use of ocean DOC is also relatively unimportant, but it is quantified here. The major source of heterotrophy for both of these systems is this excess organic carbon coming from the river. So in the Duplin, 75% of aquatic NEP is coming from the marsh. So GPP, it's 295 of net export compared to 407 GPP, and that's much greater than the calculated level of net ecosystem production. So we only need 211, and we're coming in is 295 from the salt marshes. For Plum Island, the NEP is actually so Plum Island, it's greater than the GPP, 452 versus 297. So the allochthonous carbon is even more important there, and it's much, much greater than the NEP. So Plum Island 452 versus the net ecosystem production of minus 221. So marsh organic carbon inputs in excess of estuarine demand at the Duplin and the Plum Island means there's got to be some outwelling to the ocean. So both systems export marsh organic carbon to the ocean. For the Duplin, about 114 grams carbon per meter square is exported to the coastal ocean. There's also a significant amount of DIC, which is also a form of blue carbon export, because that gets into the ocean, you can get into the deep water, and it's out of circulation for a while. For Plum Island, the export is much higher, 442 grams carbon per meter square per year. 148 of that is just passed through from the river, and 294 comes from either marsh or excess algae in the water column. So for Georgia, at least, we know the nearshore region is also heterotrophic. A lot of my studies when I was down at Sapelo, I was actually working offshore to determine what the offshore level of metabolism was. And it requires substantial amounts of organic carbon to fuel the heterotrophy that extends out to the edge of the coastal boundary layer, which is about 15 kilometers offshore. Okay, the last thing I want to talk about are these regional budgets that were produced by Maria Herman, Ray Najar, Lisa Marie Wyndham Meyer back in 2015-18. So here's one from Lisa Marie's paper in 2018 for the continental United States. I hate these acronyms, but they've looked at tidal wetlands, estuaries, and the flux of carbon between these and the atmosphere, how much is buried in the sediments, how much is brought in by the rivers, how much is exported to the show. So they're important because they show the contribution of coastal systems to global carbon budgets. They illustrate the process in organic inputs from terrestrial watersheds. They calculate what the combined export of carbon to the ocean is, and they help us better understand some aspects of the anthropogenic change. But a lot of the numbers from here are not directly, most of the numbers are not directly measured. So in Maria Herman's study, she actually had 51 estuaries along the east coast of the estuary, and they came up with budgets from all these. But mostly it's made, they're derived from models. And the model's average condition is so much different than these tidal marsh dominated systems that I'm looking at and that are so critical in the global blue carbon budgets. For example, at the continental scale, the ratio of wetland area to aquatic area, I'll learn maybe, is only 0.23 to 1 versus for us, it's 2.4 to 2.7 to 1. The water residence time is 15 months for the Gulf of Maine water, 5 months for South Atlantic Bight estuaries. Compare that with only 0.1 to 2 months for Plum Island and the Duplin, okay? I mean, the majority of the water at Plum Island has a residence time of less than a day. The DIN to TOC loading ratio, which is critical for Herman's calculation of net ecosystem production in the water column, for these two systems, it averages 0.03 to 0.05 for the Gulf of Maine and South Atlantic Bight. Yeah, for Plum Island, you know, it's several orders of magnitude. It's 0.00003, even though, you know, the Plum Island watershed, it's in the outskirts, it's in the bedroom community of Boston. It's in the Boston metropolitan area. It's heavily urban, 50% urban, but the water quality getting into that estuary is pretty high. Interestingly, Herman came up with an estimate of how much organic carbon is coming from the estuary, and she used the Sparrow model. So the Sparrow was developed by USGS to calculate river processes, river watershed processes. And she applied it to a tidal marsh and came up with these results that she concludes that tidal wetlands contribute 15% to Gulf of Maine and 40% to South Atlantic Bight total allochthonous organic carbon inputs to estuaries. Whereas we found for our salt marsh dominated systems, 70% came from the watershed for Plum Island, 83% for the Duplin. The burial, the percentage of total organic carbon inputs that are actually buried on average for her study, 6 to 2%, for us, 0.4 to 3%. Net ecosystem production on average for Gulf of Maine was -48 and South Atlantic Bight -85. Our numbers are -221 and -111. Indeed, our values for this net ecosystem production are outside her 95% confidence limits. And I would have to say, you know, those marshes at Sapelo are the most extensive salt marshes in the entire East Coast. So the East Coast does not include the Gulf of Mexico, obviously. And Plum Island has the most extensive salt marshes in all of New England, anything above Long Island Sound. So these are these are not, you know, unusual systems. This is the sort of relationship that Herman used to calculate what net ecosystem production in aquatic water bodies and in estuaries was. And as you can see, it's a pretty familiar equation. It's like a Michaelis-Menten or a growth equation, but this would be, you know, the maximum growth rate. And here's like, you know, for a Michaelis-Menten, there's your half saturation constant. So it's this hyperbolic relationship. But, you know, where does what drives the shape of this relationship here? You think it has anything to do with these sites here? So these triangles are Merle tanks. You know, there's Scott Nixon's et al.'s Merle tanks and Peelson. And then here's Chesapeake Bay, main stem Chesapeake Bay. Here's another place on Chesapeake Bay and Delaware Bay. So when you look at this equation, indeed the constant, you know, the baseline value in this equation, the C1, is lower than the value that we measured for Plum Island and for the Duplin River. So we're lower than 20 moles of carbon per meter square per year. Okay, the last thing I want to get into are a couple other sets of numbers that are used in these global budgets. And they are these three numbers. So burial, this is a number that a lot of these budgets that are put together on a regional basis rely on for the rate of carbon sequestration burial in salt marsh soils, 242. That comes from Yang and Lee, however you say that correctly, and also, you know, Gale's study. So 242. flux tower measures. So I showed you the two flux tower net E numbers for Plum Island and the Duplin, and Lisa Marie has done this similar work out in California at some of those marshes. And we're all around 200, 250. Very, very different than what we thought based on, clip plots and all that sort of stuff. DIC export, 235. Ray Najar is really fond of this number. And then organic carbon export, this is the number that that Herman's Sparrow model predicts is allochthonous carbon coming from the salt marsh into the tidal creeks, all right? Okay, so let's look at these. Whoops. Yeah. Okay, so I have two NEPs here. Here's NEP1. Let's focus on NEP. So one way to calculate, I mentioned earlier, you calculate NEP as the balance between GPP and respiration. Okay, and I also said, the flux tower, is only one part of that respiration term. You have to also add in how much DIC is lost. Well, when you take this 235 and you subtract that from the net ecosystem exchange, you get an NEP. So you're actually increasing the amount of respiration, right? This is unmeasured respiration that the flux tower does not see. So when you increase your respiration that much, there's no NEP left. It becomes a negative number. Yet we still know that there's burial going on and there's organic carbon export going on. So where's this 235 come from? It comes from two studies. It comes from Jim Morris's and Gary Whiting's study where they measured DIC concentrations at North Inlet. And yeah, they're real high. And then Jim calculated, well, how much is diffusing into the overlying water and coming out? Okay, so that's a real, that's the kind of number we would come up within a bar in like 5 minutes, and okay, and put on a napkin. And Alec Wong also came up with very high numbers, and he's been working in Sage Lot Pond, which is a coastal pond near Woods Hole, and that's a real measurement. But how can that possibly be? Those marshes around Woods Hole are definitely not as productive as the one up at Plum Island. So there's no way it has any higher NEE than that. So what could it be? Any ideas? What could it be from, John? It's got to be like old peat that is decomposing, that's totally out of the budget, but it's decomposing and it's producing DIC. And there's a lot of groundwater input up there. So it's not groundwater DIC, but the groundwater could be pushing this pore water that's down at the bottom of the peat layer into the tidal creeks. At least that's my conclusion. The other one is this net ecosystem production too. So the other way is, all right, what's the fate of the NEP? Well, the fate of the NEP is it's either exported or it's buried. So if we add these two numbers up, the NEP becomes 427. And that's another, totally unrealistic number. It doesn't come anywhere close to the work that Lisa Marie did incorporating a flux tower, or we did at Plum Island. So if that was the actual rate, so using an average soil organic carbon density of 2.7 grams carbon and a sea level rise rate of 3.6 millimeters per year, that would give us about 100 grams carbon per meter square per year, not 242. And it's similar to the rate we got of 111 at Plum Island. To get 242 with this carbon density, we'd have to have 9 millimeters per year of accretion. So I think that puts some stuff in perspective. The last slide I want to conclude with is we are relying on these numbers, either the 242, like you're coming from global syntheses, or from detailed studies we're showing here. I'm really questioning those global syntheses, their validity. We also, this might not all be Spartanic carbon. So we have 42 coming in from the side, right? We know some of it might be ancient peat, but some of it could be from the watershed, some of it could be from estuary primary producers. So there's a lochthonous carbon getting up onto the marsh. Now, the seagrass people know that seagrass beds collect all kinds of organic carbon. They always combine their burial studies with C13 studies so they can separate out the seagrass from everything else. We're going to have to start doing that for salt marshes. And then there's also this erosion. When we incorporate that erosion into the budget, it becomes very important. So we start out with 42 in, 32 out erosion, and burial is 111. So we have to correct that 111. We should be subtracting the 42 in because it's not the NEP. It's not really blue carbon. And we should account for that erosion. When you come up with those two conversions, it turns out the burial rate is only 37. And that's 17% of the rate that's actually used in those global budgets. So I'll leave it at that. My conclusion is blue carbon is challenging to quantify, and current global estimates might be optimistic about its magnitude and relevance to global CO2. And, there's just as many questions about the estuarine carbon budget now as there were after Teal's study or after John's study. And by the way, John was my major professor for both my master's and my PhD. So I was indoctrinated early on. I did work for Jim Gosling for 3 years in between my master's and PhD. And they were perhaps my best years ever. No classwork, no term papers to hand in, these guys had me take P-Chem, when I was working on my PhD, it's like this guy, his grades are looking a little bit too good. Let's give him P-Chem, I still aced it. All right, so thank you very much.
Any questions? We have a few minutes left.
Yeah, bring them on.
Take attention. Go ahead. No, Bruce
Low degrees of natural channelization. Well, it's a pond. It's a coastal pond bay, and then on the outskirts of it, there are some fringe marshes, and it's not a very well defined drainage creek network. You're right. Some of it has to do with old ditches. Yeah, so all those coastal ponds, their connection to Vineyard Sound has been reduced. They put roads and stuff over those little inlets. They're trying to restore that tidal circulation, but I don't think that has any influence on the source of this DIC that's being produced.
So some of the bigger, they have been compared to the two models in two places. One is to have a DIC export.
Oh, okay. So you're right. So for Plum Island actually has an import of DIC. So the water goes up onto the marsh and there's less DIC coming out than goes out. And Nat Weston has been studying that extensively for like the last 4 years or so. And he's done, a whole lot of 12 and 24-hour tidal cycle flux studies of water going in and out of, it's not the smallest tidal creek that we kind of focused on, like a first order tidal creek, like we did up at down at the Duplin. They're more like second or third order tidal creeks. They're much, they're like from here to the door. But because of all the ponding, there's a lot of macroalgae and macrophytes in these shallow ponds up on the marsh surface. So the thought is that they become carbon depleted very early on in the day, very high rates of primary production. You can see bubbles coming up off the mat, and we think that that's a sink for some of that DIC.
When we look at DIC lateral export, it's very hard to scale it up because the lateral exchange is on a linear basis, whereas everything we do is the area of the marsh. So how do you scale up DIC lateral export?
So, so we did it two ways. One, we just focused on the whole Duplin River itself. And we established stations down the length of the Duplin to calculate what the gradient in DIC is. And then we know what the horizontal dispersion coefficient is for that system. We can calculate how much of that is kind of exported with each tidal cycle. And Alec Wong and Wei-Jun Kai were the first ones to do that at the Duplin. And they were the first ones to draw attention to the salt marsh being a source of a lot of this DIC. Now, their conclusion was based on the fact that they did some BOD bottle respirations, and the DIC production in that bottle in the dark was not nearly as great as the amount that they're seeing exported from the Duplin River. They contributed, all right, there's got to be another source. It's got to be the marsh. Well, 50% of the respiration is benthos, in shallow water systems, it's 50% down here and 50% in the water column. So their conclusion wasn't based on real fact. So we went and looked at that first order tidal creek that drains completely at low tide. You saw there were a bunch of black dots around that. So we went to that tidal creek and we watched the water come up onto the marsh, and we put stakes all around where that water stopped flowing and where it met up with, say, water from a different tidal creek. So we know what the area that was flooded from that particular marsh. So we knew what the area was. We knew we didn't need to know the depth of the water, but from knowing the area, we could calculate what the exposure to the atmosphere, and we could calculate air-sea exchange. And then when we measured the total mass balance for the DIC and the water going in and out, we just divided it by the total area that was flooded with a particular tide. So we have very good elevation data from there. So we have two ways of doing it. One that's kind of draining the entire salt marsh estuary, because we took gradients along the length of the Duplin, and the other one just to get the marsh component of that total. Does that make sense?
All right, we are running out of time, so I don't have any questions from the people in Zoom. So, Chuck, I want to thank you again for coming today, and let's give them a we have lunch.
Great to see all you guys. Good to be back at LSU.
Victor, how was my afternoon?